In this film, let's take a look at how the ancient geocentric view of the world was replaced by the heliocentric model in the early modern era, the people involved and the role played by Kepler's laws of planetary motion. Since ancient times, it was believed that the Earth was at the center of the cosmos and that the planets, including the Sun and Moon, revolved around the Earth in spheres. The fixed starry sky was seen as eternal and unchanging. This worldview was still considered valid 1,500 years later, towards the end of the Middle Ages. In the end, it was not just a scientific model, but a strict religious dogma. Anyone who deviated from it questioned the order of the world and ran the risk of being severely persecuted. In 1543, Nicolaus Copernicus published his main work, De Revolutionibus Orbium Coelestium, according to which the planets, including the Earth, revolve around the Sun. Copernicus was already 70 years old when it was published and died just a few months later. He could therefore not be prosecuted for this. His heliocentric view of the world, which explained the motions of the planets much more simply and better than the common geocentric model, had already worked out 3 decades earlier. At that early stage, he had presented it to only a few scholars in a small circle. However, he only dared to publish it shortly before his death. Giordano Bruno went even further than Copernicus. Bruno developed the idea that the fixed stars could be distant suns, also with planets orbiting around them. He held the view that the universe was infinite and had no center. Giordano Bruno was burned at the stake as a heretic in Rome in 1600. The most important astronomer of the late 16th century was the Dane Tycho Brahe, at a time when telescopes did not yet exist. He developed instruments and methods for the precise measurement of planetary positions. No one else could match his accuracy, and his many years of precise records later formed the basis for the 3 laws of planetary motions discovered by Johannes Kepler. Tycho Brahe developed a worldview that was intended as a compromise between the geocentric and heliocentric models. In his model, the Earth is still at the center and is orbited by the Sun. However, in his model, all other planets revolve around the Sun, not the Earth. In 1572, Tycho Brahe observed a new star in the constellation of Cassiopeia, as bright as Venus, which had never been seen there before. Today we know that it was a supernova. At the time, it appeared like a new star in the firmament. A miracle, one of the greatest since the beginning of time, because since Aristotle the fixed starry sky was considered eternal and unchanging. Based on this observation, Tycho Brahe realized that this ancient idea could not be correct. In November 1577, a comet appeared in the sky, as bright as the moon and with a very long tail. According to the conventional view of the world, comets were considered to be phenomena in the Earth's atmosphere. Tycho Brahe took precise measurements of the comet's positions and also collected observation data from other astronomers. According to his calculations, the comet traveled far beyond the orbit of the Moon, passing close to Venus, which had not been considered possible until then. The precise observations of the supernova of 1572 and the comet of 1577 established Tycho Brahe's reputation as the most important European astronomer of his time. He was initially supported by King Frederick II of Denmark-Norway, who provided Brahe with an island and an observatory. Later, Emperor Rudolf II succeeded in bringing Tycho Brahe to his court in Prague as imperial mathematician and astronomer. In 1596, Johannes Kepler published his first work, The Mystery of the World. He was convinced that there was a mathematical relationship between the planetary orbits. His initial approach was to represent the relationships using nested polygons and spheres. Although this approach turned out to be wrong a few years later, it aroused the interest of Tycho Brahe, who, however, found the proposal too theoretical. Brahe favored the direct measurement of actual conditions. However, he needed someone to support him in the mathematical evaluation of his observations. Brahe lobbied Emperor Rudolf II to employ Johannes Kepler as his assistant. At the Imperial Observatory in Prague, Kepler familiarized himself with Brahe's measuring methods and saw his detailed observation records. A short time later, Tycho Brahe died unexpectedly and Emperor Rudolf II appointed Johannes Kepler as the new imperial mathematician and astronomer. After Tycho Brahe's death, Johannes Kepler devoted himself above all to analyzing the orbit of Mars, because Mars deviated most clearly from the previously assumed circular orbit. This work was interrupted in 1604 by a new celestial spectacle. At the end of October 1604, near the planets Mars, Jupiter and Saturn, which were in the constellation of the Serpent Bearer, a brightly shining star appeared that had never been seen there before, another supernova, just 32 years after the supernova observed by Tycho Brahe in 1572. In the evening sky, the new star sparkled like a brilliant and, after a few days, shone brighter than Jupiter. Kepler determined the position of this particular celestial body and realized that it belonged to the realm of stars. It could therefore neither be a comet nor an atmospheric phenomenon. This was further proof that the fixed starry sky could not be eternal and unchanging. After a few months, the new star increasingly faded and was no longer visible after a year. Kepler realized from this that stars can come into being and fade away again. Kepler now turned his attention back to analyzing the orbit of Mars. This posed the problem that Mars was observed from the Earth, which also revolves around the Sun. If you don't know the shape of the Earth's orbit, you cannot directly deduce the actual orbit of Mars only from its observed positions in the sky. In 1605, Kepler succeeded in identifying both the orbit of Mars and the orbit of the Earth as ellipses. In both cases, the Sun is not directly in the center, but in one of the two focal points of the ellipse. Kepler was able to determine the elliptical orbit of the Earth by triangulating it with Mars, the Sun and the background of the fixed stars, based on 4 orbits of Mars documented by Tycho Brahe. Now Kepler was also able to determine the orbits of the other planets as ellipses. He published his first law of planetary motion in 1609 in his groundbreaking work, Astronomia Nova. It forms the basis for the modern understanding of our solar system. The Astronomia Nova also contains Kepler's second law. He recognized that a planet moves faster in its orbit when it's close to the Sun and slower remote from the Sun. This means that equal areas of the orbital plane are swept in relation to the Sun, at equal time intervals. When the planet moves from A to B, the triangle formed by A, B and the Sun is equally large as the triangle formed by C, D and the Sun if these two distances A, B and CD were traveled in the same time. In 1608, Hans Lippershey invented the telescope in the Netherlands. News of this invention quickly spread throughout Europe. A short time later, Galileo Galilei built his own version of the telescope and used it to make observations of the sky. At the beginning of 1610, he discovered the 4 large moons of Jupiter, which clearly orbited Jupiter and not the Earth. The Earth could therefore not be the only center of cosmic movements. Kepler and Galileo made contact with each other and exchanged the results of their research. Kepler developed an improved telescope and used it to carry out his own observations of the sky. In 1619, Johannes Kepler published his second major work, The Harmonies of the World. It contains Kepler's third law. This can be used to calculate a planet's mean distance from the Sun relative to another planet, for example relative to the Earth, from its orbital period. Put simply, the longer the planet's orbital period, the further away it is from the Sun. Kepler's third law states that the ratio of the orbital periods of the two planets T1 by T2 squared is equal to the third power of the mean solar distances of the two planets alpha 1 by alpha 2. This formula can be simplified by setting the orbital period T2 for the Earth equal to 1 solar year and alpha 2 for the mean solar distance of the Earth equal to 1, which corresponds to 1 astronomical unit. Converted, this means that the mean solar distance of the second planet is the cube root of its squared orbital period. Let's take Mars as an example. Mars takes 1.881 years to complete one orbit around the Sun. This squared is 3.538161 and the cube root is 1.524. Mars is therefore on average 1.524 times away from the Sun, compared to Earth. Venus needs 0.6152 years for one orbit. She is therefore on average 0.723 Earth distances away from the Sun. Mercury takes only 0.241 years and is therefore only 0.387 astronomical units away from the Sun. Jupiter takes 11.86 years to orbit the Sun. This means he is 5.2 times away from the Sun compared to Earth. And Saturn needs about 29.5 years. His average distance from the Sun is therefore 9.5 Earth distances. With his third law, Johannes Kepler was able to calculate the actual proportions of the planetary orbits in our solar system. He assumed that an unknown force, similar to magnetism, emanated from the Sun, which would force the planets into their elliptical orbits. At the end of the 17th century, it was finally Sir Isaac Newton who explained Kepler's three laws of planetary motion with the gravitation of masses and generalized them with his law of gravitation. Now the interactions of several celestial bodies with each other and orbits of similarly heavy celestial bodies could be calculated in general. Several scientists were therefore involved in overcoming the ancient world view and creating our current knowledge of the universe. Johannes Kepler played a major role in this.